Now here is something that came up in relation to testing, and that's working with legacy code. In this particular topic, we'll have a look at the whole idea of legacy code, which is a type, not a date. We'll have a look at the hidden dangers of legacy code, and we'll review the idea that life is much less difficult if there are tests. We'll have a look at the smallest possible set of tests. Now, this particular talk was taken from Working Effectively with Legacy Code by Michael Feathers. And it was such an interesting talk, and because most of you are going to be working with code that you inherit as opposed to new code that you develop, that I thought it was worthwhile to have a look at. So let's look at the first thing. Legacy code is a type, not a date. But most of the time we think of legacy code as you know, that mainframe software that was written back in the 60s and 70s by people who are now retired. Well, yeah, it probably is. But legacy code is also code that might have been written yesterday for which there's no documentation. Right? So you've got no idea what it does. The various characteristics that Michael Feathers lists is that there's no documentation, the internal workings itself are not particularly clear, no one knows how it all fits together, and there are no tests or test suites. Okay, so this is possibly badly constructed code, and there's no help to try and make it easier for you. So the observation there is, well, software is allowed to be like that, and as long as it keeps working, not a problem. And there's a whole lot of code that has kept working for a long time, but it's still a problem. The hidden dangers of legacy code. Well, I have had some experience with this. The dangers are you can't be confident that you're making a change. You change one instruction somewhere, you have no idea what effect that change is going to have because there are so many hidden connections and hidden effects of the thing. So this is a danger of legacy code. It's difficult to estimate the size and duration of a change because you have no idea what one change is going to set off. And there is an anecdote that I think they call it the Roach Hotel. Engineers check into the code and they never check everything because they start in fixing something and it uncovers something else, and they have to fix that, and they have to fix that, and they have to fix that. Like fixing a leaky water tank, it doesn't work. There is also a fear in these things of introducing a subtle bug. Obvious bugs we don't mind because at least they crash and we can find them, but introducing a subtle bug, that's a problem. All right. Now, the whole point about that, as Feathers points out, is that life is at least helped if there are some tests. It's much less difficult with tests. So an effective set of tests enable you to say what the system does actually do, or what it's supposed to do. And you can run these tests so that you can check that some change you've made at least has been made without untoward side effects. Now, what is the smallest possible set of useful tests? We want, if you've got old legacy code, you don't want to sit there trying to devise all possible tests because you don't know they're right. What you want is the minimum set of tests you need to assure that a change you've just made hasn't smashed things. So you want tests enough to provide an invariant to the code base. Right? We'll deal with an invariant in a moment. An invariant lets you know when you've changed the behavior of the system. The correct behavior is defined by what the code did yesterday, not by some external specification. I mean, this gets back to the idea that the code does what the code does, not what it was supposed to do. It's implemented the way it is. Users will become accustomed to the system's behavior, bugs and all. Right? Rigorous testing will uncover numerous bugs. And the problem is, what are you going to do with those bugs? Now, an inflection point is a narrow interface through which a set of classes It's something through which you can tell large sections of the system are working. So in this illustration, there is this concept of a customer, and quite a great deal of information goes through the customer. So the customer itself changes to information recorded about the customer, or changes relation to things done by the customer, tend to point out when something else in the system has changed or become worse. So a change to, in that case, a change to the price of a movie or rental will have an effect on the customer. So you can make a change in there, test them, but then test customer and see if what you've changed has made an unexpected or unwanted change in the customer. So covering an inflection point involves writing some tests for it. Often you have to break dependencies. All right? The key assumption is that code changes behind the inflection point will not affect the system without going through the inflection point. So that's what I was saying. The changes made to the pricer, movie, or I forgot the other one, will be reflected in something in the customer if they've altered something. So testing customer checks that other parts of the system haven't changed. So a summary then for legacy code is that legacy code is code without the means to modify it safely. Pretty good description for legacy code. A good set of tests allow you to know when and how a modification has changed the system. It's not that you can make changes safely, but that you can detect when a change has set off some other unexpected, unwanted effect. Identify inflection points and test for changes in their behavior, if you can, all right? You may have to break dependencies between the inflection point and other parts of the system in order to get a good inflection point. So that's legacy code.